Alright, so this is section 8.1, which is systems of linear equations. So you might remember from earlier in our very first unit that any equation that can be written in the form ax plus by equals c are straight lines, and when you graph them they're called linear functions. Well, if you have two or more of these equations, then what you end up with is what's called a system of linear equations, or a linear system. Now, solutions to systems are solutions that work in all of the equations of the system, meaning that you're going to get an ordered pair, an x and a y, and it has to work in all of the equations. It can't just work in one, it has to work in all of them. So here in example 1, we're going to consider the system x plus 2y equals 2 and x minus 2y equals 6. And we're going to determine if the ordered pairs that they've given us are solutions to the system. So we're going to start here with 4, negative 1. We're going to take that and we're just going to plug it into this equation. So 4 plus 2 times negative 1, does that equal 2? If we go to our calculator here, 4 plus 2 times negative 1, we get 2. So 2 equals 2. Check. It works in that first one. I'm just going to clear that out real quick. Alright, let's check the second equation. 4 minus 2 times negative 1, does that equal 6? Okay, and go to my calculator. 4 minus 2 times negative 1, and we get 6. So 6 equals 6. Check. Since it worked in both of them, since it made both of them true, we can say that 4 comma negative 1 is a solution to the system. Okay. Let's try this other point. We have another point over here, negative 4, 3. So we're going to try plugging into the top equation first. Negative 4 plus 2 times 3, does that equal 2? So negative 4 plus 2 times 3, we get 2. So 2 equals 2. So it works okay in that top equation. Let's try the bottom equation. Negative 4 minus 2 times 3, does that equal 6? So negative 4 minus 2 times 3, we get negative 10. Does negative 10 equal 6? No, those are not equal. So that one did not work. So since that one did not work, we can say that negative 4 comma 3 is not a solution to the system. Okay. And so that's how you check if your answer is a solution to the system or not. You just plug it into the equation and you just see if it makes the equations true or not. Now, how do we find these solutions to the systems of equations? Well, there's actually a number of different ways you can do it. I've listed 3 of them right here: elimination, substitution, and graphing. We're going to focus primarily on substitution and elimination because those are the 2 easiest strategies and most frequently used strategies for solving these systems of equations. So let's start with substitution. In order to solve a linear system by substitution, step 1, you need to solve either one of the equations for one of the variables in terms of the other. Meaning, you either need to get y equals something with x in it, or you need to get x equals something with y in it. Now, if you already have one of those, like one of your equations is already written like that, you get to skip this step. Right. Step 2, substitute the expression that you found in step 1 into the other equation. So basically, in step 1, if you have y equals something with x, then in step 2, you're going to replace the y in your equation with whatever your something of x is. When you do that substitution, that will change the equation so that it now only has one variable, and you can solve it. And that's what step 3 is. Step 3 is solve the equation, figure out what that one variable equals. Step 4, back substitute the value you got in step 3. Take that answer, plug it back into one of your equations from step 1, and figure out what the other variable is. Once you know both variables, check your solution in both of the equations, make sure it does work for both. Okay. So example 2 here asks us to solve this system of equations with the substitution method. 5x minus 4y equals 9, and x minus 2y equals 3. Now looking at these two equations, the second one is easy to isolate a variable. It's pretty easy to isolate this x. All I have to do is take the 2y and add it over. So I could rewrite this equation as x equals 2y minus 3. Just take the 2y and add it across. So that's my first step. I've now solved this equation so that I have x equals something with y in it. Okay. Step 2, I'm going to take this equation, I'm going to circle here in blue, I'm going to take it and I'm going to substitute it in here on this equation. So I know what x equals. X equals 2y minus 3. So here where I see an x in this equation, I'm going to plug in the 2 minus 3. So I'll have 5, and then instead of this x, I'm going to write 2y minus 3 minus 4y equals 9. Distribute the 5 into the parentheses. 5 times 2y is 10y. 5 times negative 3 is negative 15. Minus 4y equals 9. Combine like terms. 10y minus 4y is 6y. Minus 15 equals 9. Add the 15 across. So 6y equals 9 plus 15. That's 24. And then divide both sides by 6. We get y equals 4. So we know half of our answer. Our answer is going to be something, comma, 4. But I need to know the x. Well, to find the x, take this y you just got and substitute it back in over here. So we'll have x equals 2 times, and instead of y, we're going to write 4. So 2 times 4 is 8. 8 minus 3 is 5. So here's my answer, 5, comma 4. Now I boxed it in. I probably should check it first. So what I'm going to do is I'm going to plug it into each of these equations. So on this top equation, I have 5 times 5 minus 4 times 4. And that does equal 9, so it works in that one. If we take it and plug it in the bottom equation, that would be 5 minus 2 times 4. And that gives us negative 3, which works in the bottom equation. So that solution does work for both of them, so it's an okay solution. Okay. So it's not too bad. Substitution method is not terribly challenging. Let's look at another one of these. So this one asks us to solve by the substitution method. 3x plus 2y equals 4, and 2x plus y equals 1. This second equation is pretty easy to solve for a variable. It's pretty easy to get the y by itself. Just take the 2x and subtract it over. So y equals negative 2x plus 1. So just took that and moved it over. Now that we have y equals something with x, our next step is going to be substituted in. So I'm going to take this and I'm going to plug it in for the y here on this other equation. So I'll have 3x plus 2 times, instead of y, I'm going to write what y equals. So it equals negative 2x plus 1, and then that's equal to 4. Distribute the 2 into the parentheses. So 3x, 2 times negative 2x is negative 4x, and 2 times 1 is 2, equals 4. Combine like terms. 3x minus 4x gives us a negative x plus 2 equals 4. Subtract the 2 across. Negative x equals 4 minus 2 is 2. And then divide both sides by a negative 1. X ends up equaling negative 2. So I know half of my answer is negative 2 comma something. To find the y value, I'm just going to take this x that we found, and I'm just going to plug it back in up here for this x. So I'll have y equals negative 2 times negative 2 plus 1. So y equals negative 2 times negative 2 is positive 4 plus 1 is 5. So here's my solution, negative 2 comma 5. And again, I want to check it in my equations. So 3 times negative 2 plus 2 times 5. It gives me 4, which matches up with what we have here. And then 2 times negative 2 plus 5. That gives me 1, which matches up with what we have there. So it did work in both equations, so we know that that is a good solution to the system. Okay. So that's how substitution works. The other method we're going to look at is the elimination method, which is also sometimes called the addition method. Okay. In the elimination or addition method, the first step is, if necessary, rewrite both equations so that they are in the form ax plus by equals c. They need to be in that form in order to do this method. It has to go ax plus by equals c. Step 2. If necessary, multiply one equation or both equations by an appropriate non-zero number so that the sum of the x coefficients or the sum of the y coefficients is 0. Basically, you're wanting to eliminate the x's or the y's when you add the two equations together. And so you want the coefficients to be the same number but opposite signs, so that way when you add them together they will cancel out. Once you have the coefficients set up, step 3 is to add your two equations together. When you do this addition, the sum will be an equation that only has one variable in it. Step 4, solve that equation, figure out what that one variable equals. Step 5, take that answer and back substitute it into either of your equations that you had up at the beginning, and then that'll get you your other variable. Step 6, remember to check your answers, make sure you're doing it right. Alright, so let's look at this. Example 4 here asks us to solve this system by the addition method, which again, remember that's also the elimination method. So our system is 3x plus 2y equals 48, 9x minus 8y equals negative 24. So first thing, are they in the form ax plus by equals c? Yeah, both of them are already in that form, so we're good there. Second thing, do I have it set up so the coefficients can cancel out on either the x or the y? Well, if I added right now, the x's would end up with 12 and the y's would end up with negative 6. So right now they don't cancel. So I need to multiply one or both of these equations by a number. Now the easiest thing to do is multiply this equation by 4. So I'm going to just rewrite the bottom equation, 9x minus 8y equals negative 24. But on the top equation, I'm going to multiply it by 4. So 3x times 4 is 12x. 2y times 4 is 8y. And 48 times 4, I don't know that, so I'm going to do that really quickly over here. 48 times 4 is 192. Now, if I was to add these things, this 8y and this negative 8y would cancel each other out. And so that's what we're going to do next, is we're just going to add these two equations together. So 12x plus 9x is going to be what, 21x? 8y, negative 8y, those will cancel. And then 192 plus negative 24. Well, I'm going to take that 192 and I'm going to add negative 24 to it. I get 168. And then we would divide both sides by 21. And we get x equals 8. So there's half of my answer, 8 comma something. To find my y value, I'm going to take this 8, and I'm just going to go back and plug it back in up here for the x. So I'm going to have 3 times 8 plus 2 times 2y equals 48. 3 times 8 is 24, plus 2y equals 48. Subtract the 24 across, so 2y equals 48 minus 24 is 24. And then divide both sides by 2, and you get y equals 12. So my solution looks like it is 8 comma 12. Take it, plug it back in, and make sure it works. 3 times 8 plus 2 times 12. That does equal 48, so it works in the first equation. And the second one, 9 times 8 minus 8 times 12 gives us negative 24, which, yep, that matches the second equation. So since it worked in both, we know that is the correct answer, a correct solution to this system. Okay. Example 5 is another elimination method. It asks us to solve this one with the addition or elimination method. We have 2x equals 7y minus 17, and 5y equals 17 minus 3x. First off, are they in the correct form? Are they in the form ax plus by equals c? No. The x's and y's are on opposite sides. So I need to take the 7y and move it over. I need to take this negative 3x and move it over. So this first equation is going to become 2x minus 7y equals negative 17. The second equation, when I move the 3x over, it's going to become 3x plus 5y equals 17. Okay, so they've both been moved, so now they're in standard form. Second step, we look at the coefficients. Right now, if we added it, we would have 5x and negative 2y. So nothing cancels right now. So I need to figure out a way to cancel. Well, this one's a little more complicated. I would need to get a common number either for 2 and 3 or a common number for 7 and 5. And I would also want them to have opposite signs. So what I'm going to do, I think I'm going to multiply this top one times a negative 3. And I'm going to multiply this bottom one times a positive 2. So that way I have 2x times negative 3, which gives me negative 6x. Negative 7y times negative 3 is going to give me positive 21y. And negative 17 times negative 3, I don't know that off the top of my head, but I can find it. It is 51. Down here on this one, 3x times 2 gives me 6x. 5y times 2 gives me 10y. And 17 times 2, I believe it's 54, but let's just verify. 17 times 2, oh, so 34, not 54. Wow, that was way off. But now if you look, the coefficients, it's the same number here, but they're opposite signs, so they will cancel out when we add these equations together. So negative 6x and positive 6x, those cancel. 21y and 10y will make 31y. 51 and 34, it's going to be 85. And then we can divide both sides by 31. So 85 divided by 31 It doesn't go in really nice, so I'm just going to have my calculator change it back to a fraction, which is still 85 over 31. Okay. So there's my y, as ugly as it is. So my answer is going to be something, comma, 85 over 31. To find my x, I need to plug this back in for y in one of my original equations. I think I'm going to take this, and I think I'm going to plug it in for the y right here. So I'm going to have 5 times 85 over 31 equals 17 minus 3x. So I need to take this 85 over 31 and multiply it by 5. Which, again, I'm going to get a fraction for that. So that's 425 over 31 equals 17 minus 3x. Subtract the 17 across. So minus 17. And again, I'm going to get a fraction. So it's negative 102 over 31 equals negative 3x. And then I'll divide by negative 3 to get the x by itself. So divide this by negative 3. Again, give me a fraction. So it's 34 over 31. So there is my solution to this system. Again, you want to check it. I'm going to check it using our rewritten ones because it'll be easier to check that way. So 2 times 34 over 31 minus 7 times 85 over 31. That equals negative 17, which that's what it's supposed to equal. Excuse me. For our second equation, 3 times 34 over 31 plus 5 times 85 over 31. That equals positive 17, which is what it's supposed to equal. So again, because it worked in both equations, we can feel pretty good that that is our solution to the system. Okay, so that is elimination. Now, here is the thing. Not all systems have solutions. There's actually 3 different possibilities that you can end up with when you are solving a system. The first one is what we've looked at so far. When you solve the system, you get an answer. You get x equals this and y equals that. So in terms of number of solutions, you get exactly one solution. You have exactly one ordered pair that works. Graphically, what that means is if we graph these 2 lines, these 2 linear functions, they will intersect at that one ordered pair, at that one point. And we call this type of system a consistent system. Consistent systems are systems that have exactly one solution. Other times, though, when you solve systems of equations, the variables will all cancel out, and you'll end up with just a true statement. Something like 0 equals 0, or 5 equals 5. If you wind up with a true statement, what that is telling you is that you actually have an infinite number of solutions. It really does not matter what x and y are, that any x, y will work. You'll end up with an infinite number of solutions. Graphically, what that means is these 2 lines are the exact same line. They are right on top of each other. So any x that goes on one line also goes on the other line. We call this type of system where you get a true equation a dependent system. A dependent system is called dependent because one equation is usually a multiplication of another equation. Meaning we took one of the equations and multiplied it by 2 or something, and then that was our second equation. So that second equation, because it's multiplied by 2, it's dependent on the first one. So that's why it's dependent. The third result that we can get is a false statement. Meaning all of the variables will cancel out, but we'll end up with something like 0 equals 2, which is not true. If you get a false statement, that tells you that your system has no solution. Graphically, that means that these two lines are parallel, so they will never touch and will never intersect. And we call this type of system an inconsistent system. So with that in mind, let's look at example 6. Example 6, we have 4x plus 6y equals 12, and 6x plus 9y equals 12. We could solve this with substitution or elimination. It didn't tell us how to do it. I'm going to use substitution, and I think I'm going to try and make the x's cancel by getting a common coefficient of 12. So I think I'm going to multiply this one times 3. I'm going to multiply this one times negative 2. So 4x times 3 is 12x. 6y times 3 is 18y. Equals 12 times 3 is 36. Down here, 6x times negative 2 is negative 12x. 9y times negative 2 is negative 18y. And 12 times negative 2 is negative 24. And then I'll add these together. Negative 12x plus 12x, those cancel out. 18y plus negative 18y, those cancel out. So there's nothing left over on this side. So we have 0 equals, over here, 36 plus negative 24 is 12. So I ended up with 0 equals 12. Is that true? Does 0 equal 12? No, this is false. And because it's false, that tells me that this system has no solution. And we can say that the system is inconsistent. So sometimes that does happen. Sometimes you try to solve the system and you just wind up with something like that, and that just tells you your system doesn't have a solution. Example 7. We want to solve the system y equals 3x minus 2 and 15x minus 5y equals 10. This one I'm going to solve with substitution because they've already solved this equation for y. They already have y by itself. So what I'm going to do is I'm going to take that and I'm just going to substitute it into the y right there. So 15x minus 5 times, instead of y, I'm going to write 3x minus 2 equals 10. So 15x, we're going to distribute the negative 5 in. Negative 5 times 3x is negative 15x. Negative 5 times negative 2 is positive 10. Combine like terms, 15x and negative 15x cancel out. So I wind up with 10 equals 10. Well, is that a true statement? Does 10 equal 10? Yeah, that is true. And so what that tells us is we have an infinite number of solutions. Basically, this would be a set any x, y, such that y is equal to 3x minus 2. Now, I could use either of the equations. I just wrote the first one. But you could use either one in here. But basically, any x, y that works in this equation will also work in that equation. We can also say that the system is dependent, meaning that this bottom equation is probably a multiplication of this top equation. In fact, it is. It's a multiplication of this top one by 3, or negative 3, something like that. So that's kind of how that works. Okay. So that's linear systems in two variables. Next, we're going to move on to linear systems in three variables, which students sometimes do find a little tricky. So in three variables, that means you're going to have x, y, and z. Now, just like with two variables, you do have three possibilities that you can get when you solve these systems of equations. First off, you could get just one answer, one solution, x, comma, y, comma, z. Two, you could get no solution. It could be that these three-dimensional planes do not intersect each other, and so there's no actual solution to the system. Or, the third option, you could get an infinite number of solutions where the planes touch each other and are on the same line, and so a point on that line would be a solution to the system. Okay. Now, when you get that third option, when you get infinitely many solutions, then usually what we do is we define our equations in terms of one of the other variables, meaning we write x as some function of z and y as some function of z, and then we say z can be any number. So we say, okay, if z is 5, then x and y are this. And if z is 6, then x and y are this. So we basically make x and y be functions of z. Now again, you only have to worry about that when you have infinitely many solutions. Any other time, you don't really have to worry about it. Now, to solve a system of equations in three variables, we use the elimination method, but we actually end up having to use it 3 different times. We use it 2 times to eliminate one of the variables from 2 different sets of equations. So like if I number my equations 1, 2, and 3, then I'm going to pick a variable like x and say, hey, I want to eliminate x from 1 and 2, and I want to eliminate x from 2 and 3. Now when you do those 2 eliminations, that will eliminate one of your variables. That will get rid of your x. And so what you'd be left with is just 2 variables, y and z. So then you get to do an elimination process a third time to eliminate one of those variables, to either get rid of the y or get rid of the z. After you do the elimination process the third time, you wind up with an equation that only has one variable. You can then solve that equation and get that variable. Once you get it, then you can back substitute into one of your previous equations to solve for the second variable you eliminated. Once you have those 2, then you can back substitute again and solve for the third remaining variable, the first one you eliminated. Okay. So it's a little bit of a process, but it is totally doable. So let's look at it. So example 8 asks us to use the method of elimination to solve the system of equations x plus y minus z equals -1, 4x minus 3y plus 2z equals 16, and 2x minus 2y minus 3z equals 5. Now what I usually do first off is I number my equations to kind of help me sort this thing out. So I have 1, 2, and 3. Now I need to pick a variable to eliminate. It looks like z would be a pretty easy one to eliminate because I can just multiply this by 2 and that would cancel that one out. Or I could multiply this one by -3 and it would cancel that one out. So I think I'm going to try to eliminate z first. So the first thing I'm going to do is I'm going to eliminate z in 1 and 2. Okay. So to do that, I'm going to multiply this first equation, equation number 1. I'm going to take it and multiply it by 2. So 2 times x is 2x. 2 times y is 2y. 2 times -z is -2z equals 2 times -1 is -2. And then I'm just going to rewrite equation number 2. 4x minus 3y plus 2z equals 16.
And then I'm going to add those together. So 2x plus 4x makes 6x. 2y minus 3y, that makes negative y. Negative 2z and positive 2z cancel each other out. Negative 2 and 16 makes 14. So I get this equation that no longer has any z's in it. I'm going to label this equation A. Okay. So I've eliminated z between 1 and 2. Now I need to eliminate it a different way. So I'm going to try now eliminating the z from 1 and 3. Okay, so between this one and this one now. So to do that, I'm going to take this top equation and multiply it by negative 3. So I'm going to take equation number 1 and I'm going to multiply it by negative 3. So negative 3 times x is negative 3x. Negative 3 times y is negative 3y. Negative 3 times negative z is positive 3z. And negative 3 times negative 1 is positive 3. And then I'm going to go in and write equation number 3 down. So it's 2x minus 2y minus 3z equals 5. And I'll add those together. So negative 3x and positive 2x makes negative x. Negative 3y and negative 2y makes negative 5y. 3z and negative 3z cancel, so the z gets eliminated. And 3 and 5 make 8. And so I'm going to label that equation as B. Okay. So now I have two new equations. I have equation A and I have equation B. And these two new equations only have two variables. Then we have x and y in them. So now I need to decide how to eliminate another variable. I think what I am going to do is, I think I'm going to eliminate y's by multiplying this one by a negative 5. So I think I'm going to eliminate y in A and B. So I'm going to do negative 5 times my A equation. So negative 6x times negative 5 gives me negative 30x. And the negative y times negative 5 gives me positive 5y. And negative 5 times 14, I don't know, so I'm going to make a calculator. 14 times negative 5 is negative 70. And then I'm going to write down my B equation, which is negative x minus 5y equals 8. And then I'll add those together. Negative 30x plus negative x gives me negative 31x. 5y and negative 5y cancel. Negative 70 plus 8. Well, I've got my negative 70 there. I'll add 8 to it. And I get negative 62. Then I can solve this for x by dividing both sides by negative 31. So divide that by negative 31. We get x equals 2. So I know my answer. My final answer is going to be 2, comma, something, comma, something. So I have my x. I need to find y and z. Well, I'm going to take this, and I'm going to substitute it back in here, back into A. So I'm plugging x equals 2 into A. So I'm going to have 6 times 2 minus y equals 14. So 6 times 2 is 12 minus y equals 14. Move the 12 over, negative y equals 14 minus 12 is 2. Divide by negative, so y equals negative 2. Okay. So now I have x and y. The last thing I need is z. To find z, I need to plug back into one of my original equations. So I am going to plug x equals 2 and y equals negative 2 back into equation number 1. So I'm going to have 2 plus negative 2 minus z equals negative 1. A positive 2 and a negative 2 cancel, so I really just have negative z equals negative 1. Divide by a negative, and I end up with z equals 1. So this looks like my answer. I can check it by plugging it into these equations. So if I plug it into this first equation, 2 plus negative 2 minus 1, I get negative 1, which is what I'm supposed to get. Plug it into the second equation, 4 times 2 minus 3 times negative 2 plus 2 times 1. That gives me 16, which is what it's supposed to get. And then the last equation, 2 times 2 minus 2 times negative 2 minus 3 times 1. I get 5, and hey, that's what I was supposed to get. So it does work when I plug it into all 3 equations, so I can feel pretty good that that is a solution to this system. Again, notice we had to do elimination 3 times. We eliminated z twice, and that gave us 2 new equations. Then we took those 2 new equations and we eliminated y from them, so that left us with just x. Once we knew what x was, we back substituted into either equation A or B, so that way we could solve for y. And then we took the x and the y and substituted it back into 1, 2, or 3 to find z. And that's kind of the way the process works when you solve equations in 3 variables. Oops, sorry, scroll a little too far. So example 9, this is another one where we're going to solve a system in 3 variables. This is our last one for this set of notes. So again, we have 3 equations. I'm going to number them 1, 2, and 3. I want to eliminate one of the variables, and it looks like z would be pretty easy to eliminate. So the first thing I'm going to do is I'm going to eliminate z in 1 and 2. And I actually don't have to do anything special here. I can just take equation 1, which is x minus 2y minus z equals 8, and I can add it to equation 2, which is 2x minus 3y plus z equals 23. When I add those, x plus 2x is 3x, negative 2y plus negative 3y is negative 5y, negative z and positive z cancel. 8 and 23, that's going to be 31. And so I'll label that new equation as A. Okay. So I've eliminated z from 1 and 2. Now I need to either do it from 1 and 3 or 2 and 3. And it's actually really easy to do with 1 and 3, so I'm going to do that next. So I'm going to eliminate z in 1 and 3. And I can do this by taking 5 times equation number 1. So 5 times x is 5x. 5 times negative 2y is negative 10y. 5 times negative z is negative 5z. And 5 times 8 is 40. And I'm just going to add that to equation 2. Or sorry, equation 3. So that's 4x minus 5y plus 5z equals 53. I'm just going to add those together. 5x plus 4x makes 9x. Negative 10y plus negative 5y makes negative 15y. My negative 5z and positive 5z cancel. And 40 plus 53 gives me 93. And so that would be my B equation. So now I have eliminated z from 2 different sets of equations. So now I need to pick another variable to eliminate. I need to either eliminate x or y. And I think I'm going to get rid of y. And I'm going to do it by multiplying this by negative 3. So I'm going to eliminate y from A and B.
So I'm going to do negative 3 times equation A. So negative 3 times 3x makes negative 9x. Negative 3 times negative 5y makes positive 15y. Equals negative 3 times 31. Let's see, what is that? Negative 93. And I'm going to write down what my B equation is. So my B equation is 9x minus 15y equals 93. So when we add these together, negative 9x and 9x would cancel. 15y and negative 15y would cancel, so we have 0 equals negative 9x and positive 9x cancel. That gives us 0 as well. So we have 0 equals 0. Well, that's a true statement. There are no variables left, but it is a true statement, which tells me that I have an infinite number of solutions. So I have an infinite number of solutions. So I need to decide how I want to write these solutions. Well, one way to do it is to basically solve these equations so that way we have x and y as functions of z. And what I mean by that is take one of these equations and solve it for either x or y, and then plug it into one of the other equations and kind of solve it out. So like if I take this equation and I solve it for x, let's say, move the 5y over, we say 3x equals 5y plus 31. Divide by 3x equals 5/3 y plus 31 over 3. Okay. Take that, plug it in here for the x. Okay. So I'd have 5/3 y minus 2y minus z. Oops, sorry, I forgot something, didn't I? 5/3 y plus 31 over 3 minus 2y minus z equals 8. And then what we want to do is we want to solve this equation for y. So I'm going to move the z and the 31/3 over. So I'm going to have 5/3 y minus 2y equals z, and then I'm going to have 8 minus 31 over 3. So let's see what that is. 8 minus 31 over 3. That's, change it back to a fraction, that's negative 7/3. So minus 7/3. I'd also like to combine those two together. So let's see, 5/3, minus 2. We'll change that back to a fraction. So that's negative 1/3 y equals z minus 7/3. Take this and let's multiply everything by negative 3. So negative 3 times negative 1/3 y just gives us y. Negative 3 times z gives us negative 3z. And negative 3 times negative 7/3, it's a negative times a negative, so it's going to be a positive. 7 times 3 is 21, divided by 3 gives you 7. So we end up with this statement, y equals negative 3z plus 7. Okay. Now we're going to do the same thing, but instead of solving for x, we're going to take this equation, and we're going to solve it for y. So negative 5y equals negative 3x plus 31. So y equals 3 over 5x minus 31 over 5. Take that, plug it in for the y up here in equation 1. X minus 2 times 3 over 5x minus 31 over 5 minus z equals 8. So x, distribute this in, you'd have minus 6 over 5x plus, let's see, it's going to be 62 over 5 minus z equals 8. move these non-x terms over. We'll also combine these x's together. So I have 1 minus 6/5. So that's going to be negative 1/5 x equals, we're going to move the z over, and we're going to move the 62 over 5 over. So we're going to have 8 minus 62 over 5. Convert that back to a fraction. That's negative 22 over 5. Then what we'll do is we will multiply all of this stuff by negative 5. Negative 5 times negative 1/5 x gives us x. Negative 5 times z gives us negative 5z. And negative 5 times negative 22 over 5, it's a negative times a negative, so it's a positive. The 5's could cancel out, so we'd really just have a 22. So now, we're actually ready to write our solutions to our systems. It's x comma y comma z, such that the x is negative 5z plus 22. The y is negative 3z plus 7. And the z is z. Okay. Now, when we write it like that, what it means is I can pick any number for z, any number I want, and once I have determined that number, I can also plug it in here, and that will let me find x, and I can also plug it in here, and that will let me find y. But z can be any number, which is why we have an infinite number of solutions. I can put any number here for z, and that will change the z here, and so I end up with an infinite number of solutions. Now these ones can be a little complicated, but this is kind of the process you work with. If you end up with a true statement, you're going to have to write an equation with y in terms of z and x in terms of z, so that way you can write your ordered pair that allows you to have an infinite number of solutions. Okay? So that is it for 8.1. If you have any questions on any homework or anything like that, please feel free to send me an email.